Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be using mathematical induction to prove that the sum from r equals to 1 to n of 1 on 4r squared minus 1 is equal to n divided by 2n plus 1. This is just a continuation of the previous video I did, where we actually had to find this sum using our knowledge of partial fractions. So to prove this by mathematical induction, we start by let the statement P of n be what we are proving. So let the statement P of n be this for all integral values of n. Okay, now we need to start by verifying if the statement is true for the very first value of n. So you have to verify that the statement P1 is true. Okay, since r is beginning from 1. Now P1 is a statement. In fact, we realize that if I replace n with 1, okay, if I sum from r equals to 1 of this, I'm just going to get just the first term. So I'm just replacing r with 1. So 4 into 1 squared minus 1, which will give me 1 divided by 3. Now you realize that if I replace n with 1 in my right hand side, I'm still going to get 1 divided by 2 into 1 plus 1, which is equal to 1 divided by 3. So since this sum here, okay, is equal to 1 divided by 3, then the statement P1 is true, right? Since the statement P1 is a statement, the sum from r equals to 1 of this quantity is found by replacing n with 1 here and replacing n with 1 here and simplified. Now the next thing to do is induction hypothesis, where we assume or we suppose that P of k is true. That's the statement P of k is true. Now we write down what the statement P of k is. The statement P of k is that the sum from r equals to 1 to k of 1 on 4r squared minus 1 is equal to k divided by 2k plus 1. I'm just replacing k in the place of n. And we now have the induction step where we have to prove that the statement P of k plus 1 is true. We have to prove that P of k plus 1 is true using our induction hypothesis. Okay, now let us write down what we need to prove. So P of k plus 1 is simply a statement. The sum from r equals to 1 to k plus 1 is equal to, I just need to replace k with k plus 1. Come here and I replace k with k plus 1. If I simplify, I get 2k plus 2, then plus 1, you have 2k plus 3. This is just simplification, so you can do it on your own and you simplify. Okay, you just come and replace n here with k plus 1 and then we simplify. So this is what we need to prove. Okay, and in proving something like this, we always begin with the left hand side. So I begin with this. Alright, so this sum is basically equal to summing from 1 to the n term plus the n plus 1 term. So maybe plus the k plus 1 term. Okay, so doing that, I simply have that this sum here is equal to, now this is already true by from the induction step, that's from the induction hypothesis. So I just need to copy since the statement is true. Now what is a k plus 1 term? It is found by replacing r here with k plus 1. So I just copy this and I replace r with k plus 1 and I simplify. So we replace r with k plus 1. Okay, so if we simplify correctly, we get k divided by 2k plus 1 divided by 4 into k squared plus 2k plus 1 then minus 1. I'll just multiply. So this is k divided by 2k plus 1 divided by, now we have 4k squared plus 8k plus 4 then minus 1. but this is going to give us 3. Okay, so let us see how we can factorize the quadratic 4k squared plus 8k plus 3. Now we need to find the factors of 4 times 3, the factors of 12. Okay, that when we add we have 8, and when we multiply we have 12. What are those factors? 6 and 2. If we add 6 to 2 we have 8. If you multiply you have you have 12. So you have 4k squared plus 2k plus 6k. Since 8k is a sum, then plus 3. So this gives us, we can factorize 2k from the first 2 terms, and we have 2k plus 1. And from the next 2 terms we factorize 3, we have 2k plus 1. Now we can now factorize 2k plus 1 from both terms, and we're going to be left with 2k plus 3. Okay, so it means that I'm just going to come and write here. So we have k divided by 2k plus 1 divided by, our denominator has already been factorized into this. Now you realize that the LCM of these two things is just our 2k plus 1 times 2k plus 3. It therefore means that this sum here, which is what we are simplifying, that sum is basically equal to, so we have all of this. Let's take it down to the next page. So the LCM, okay, the LCM is simply 2k plus 1 times 2k plus 3. That's the LCM. Now you realize that when we divide with this and multiply by k, we just have k into 2k plus 3 plus 1, because it divides itself and simplifies. Okay, so that's what we have. Now if we continue simplifying, we have 2k plus 1 times 2k plus 3. The numerator is 2k squared plus 3k plus 1. We further factorize the numerator. It means 2k squared plus 3k plus 1. We find the factors of 2 times 1, factors of 2. That when we add we have 3, multiply we have 2. It's just 2 and 1. So our 2k squared, 3k is now the 2k plus k. Okay, then plus 1. So from the first 2 terms I factorize 2k, I have k plus 1. From the next 2 terms you just write it in this form, and then you can factorize k plus 1 from the 2 terms and you have 2k plus 1 left. So it therefore means that this sum here, okay, is equal to, now here is our denominator. This is the denominator, and the numerator has been factorized into this. So you realize that 2k plus 1 cancels, and what are we left with? We are left with 2k plus 3 in the denominator. And we are left with k plus 1 in the numerator. Now let us go back to see if we have arrived where we have to arrive. So we have to arrive here, so it is perfect. So we have proven that the statement is true for n equal to k plus 1. We just conclude. So we conclude, since, or let's say hence p of k plus 1 is true. Now our conclusion, we have to say, since it is true for n equal to 1 and true for n equal to k plus 1, as assumed true for n equal to k, then it is true for all n in the set of natural numbers or positive integers. That's let's just go and copy what we're proving, that this, okay, that is sum from r equal to 1 to n of 1 on 4 r squared minus 1 is equal to that, as proven by mathematical induction. As proven by mathematical induction. So that completes the induction process. Okay, thank you guys for watching. See you in the next video. If you have any questions to ask, do well to comment on the comment section. Ask your questions there. I'm going to reply to you. Share the video with your friends, like the video, and subscribe to the channel. Stay tuned for more videos. Thank you very much.